This KP calculation is from page 13 in the notes. Not as much structure this time, so we've just got a blank piece of paper. And we've been given grams rather than moles. So we've got a little bit of work to do to start with. So to work out the moles of the N2O4, we want to do the mass over the MR. So that's 9.2 divided by the MR of N2O4, which, if you work it out, conveniently comes to 92. So that means we've got 0.1 moles of N2O4, which we're decomposing. Also note that they're in a 2-to-1 ratio. So we've got 0.1 moles of the N2O4 initially and no moles of the NO2, and our information is that 70% has dissociated, which means it will be down by 0.07, which will leave us with 0.03. Over on the other side, remember they're reacting in a 2-to-1 ratio, so if the N2O4 has gone down by 0.07 moles, then this will go up by twice that amount. Which is 0.14 moles. At this point, I would just make a note of the total moles in our equilibrium, which is 0.17, just add those two together, and here I will work out the mole fractions. So I've got 0.176 for the N2O4 and 0.824 for the NO2. Hopefully we can see they come to 1. Now to get the partial pressures, we just need to times the mole fractions through by the total pressure. So the total pressure was 13.3 kilopascals, which means that the partial pressure of N2O4 is 2.34, and for the NO2 it's 11. I now want my KP expression. So we've got the partial pressure of NO2 squared over the partial pressure of N2O4, and then we'll just put those numbers in that we've got from before. So we've got 11 squared over 2.34. So to three significant figures, I've got 51.7. Hasn't asked for the units in the question, but should always really put these in if it has units. We can see we've got pressure squared over pressure. The pressure is, in this case, kilopascals, so we've got kilopascals squared over kilopascals, so that's just going to cancel down 51.7 kilopascals.